Hello everyone, good morning. We are Group 40, and this is our product quality presentation for a fully embedded 2D LiDAR autonomous mobile robot built on STM32 F446RE platform. In this presentation, we will show our system design, implementation, validation, and overall integration quality. In our team, we assign clear primary ownership to each major subsystem. Weifan, which is me, focus on system integration and autonomous control. Wang Zaiyou developed the LiDAR acquisition pipeline. Duan Mengnan worked on motor drive and encoder feedback. Zhang Zheng was responsible for mapping and pose synchronizations. And Guo Congyu supported IMU integration, user interface, and validation. Although responsibilities were divided clearly, the final system only became useful after these modules were integrated into one coherent embedded pipeline. This architecture summarizes how our robot works as an embedded system. Sensor data come from LiDAR, encoder, and gyroscope and user input. The data is received into post-estimation, mapping, and acceleration decisions, which then drive the motor control layer. At the same time, Bluetooth and OLED outputs make the internal state visible, and the whole pipeline is coordinated through IRTOS tasks, interrupts, DMAs, and queues. We would say that ROM does not build in one day, thus we design explicit design state and phase goals to achieve. On this slide, we'll summarize the main behavior demonstrated by our system for different phases in live operation. We'll first show command-to-response behavior, then autonomous explanation in mice, and finally the real-time visibility provided by our map pose and telemetry output. The focus here is not timing performance, but integration tech qualities and stable embedded operation. First, we use user command through Bluetooth, and the robot responds immediately in respect to motion and the system feedback. This demonstrates the command handling, motor control, and communication are integrated correctly. Next, we enable autonomous explanation. The robot observes surrounding obstacles, select a feasible direction using a right-hand rule strategy, and perform hand-based tuning. At the same time, the internal system state remains visible through telemetry output, including pose updates, map-related data, and autonomous decision messages. This makes the robot behavior could be explicitly observed. After we complete the scaffolding work, we are able to test our LiDAR-equipped robot car maze-solving capacities. With the previous developed visualization GUI, we could observe the frontier point of the A-star algorithm, the planned path, and result of the SLAM mapping. Based on the visual debugging, we turned a series of parameters for the robot, including the STEM grid scores and the priority settings of the A-star algorithms. Ultimately, the robot successfully navigated ultimately to the center of the maze. This slide shows how we evaluate the quality of the system beyond a single successful demo. Firstly, LiDAR telemetry allows us to verify stable scan receptions, phrasing qualities, and continuous point publication. Second, odometries and motion logs exposed encounter counts, heading updates, and drift corrections, which helped us assess repeatabilities and turning behavior. Third, map, pose, and autonomous decision logs made the interval behavior of the robot visible, so we could explain how exploration decisions were made and refine parameters based on the evidence rather than guess. In the current firmware, the car is integrated around FreeRTOS rather than a simple pooling loop. The car is not doing one thing at a time. It must receive LiDAR data continuously, listen to Bluetooth command, update motor PWM, read encoder, set for ADC value, update the driver, refresh the OLED, build a map, and make a navigation decision. If this were written as a large blocking while one loop, one slow operation could delay everything else. For example, OLED I2C refresh or Bluetooth transmission could be blocked LiDAR phrasing or motor control. FreeRTOS resolved this by separating the system into tasks with different timing and priority. The Bluetooth task handle command and telemetry traffic. The sensing task update motion states, and the LiDAR task consumes scan points. The UI task handle display and button. The stand has its own navigation task. This makes the system easier to reason about. Each subsystem has a clear responsibility and a predictable update rate. Two important features in RTOS are tasks and queues, which is adapted widely in our system. We design different tasks for different modules, such as stance task, Bluetooth tasks, OLED updating, and navigation and planning. Queues are responsible for transporting data among those tasks. that is consumed by LiDAR sensing tasks from block queues triggered by DMA half and full complete callback as an example. DMA is also very suitable here because some data streams are too frequent for CPU-driven byte-to-byte pooling. The LiDAR send a high-rate serial stream, so USART1 use circular DMA. DMA file memory in the background and interpret only notifies the firmware while half of all the buffer is ready. That reduces CPU load and avoid losing scan data while other tasks are running. AEC also uses DMA without forcing the CPU to start and wait for each conversion. The system coordinates the classic think-act pipeline by separating each stage into shadow-free RTOS tasks and connecting them with queues and shared state. In the send stage, LiDAR data is received through DMA and phrased into decision point, while encoder, ADC value, buttons, and MPU 6500 gyro are predictably sampled by sensor or UI tasks. In the think stage, these sensor inputs are fused into robot pose, obstacle or front sector state, occupation secret update, auto mapping decisions, and SLAM navigation plans. In act stage, the selected behaviors such as manual drive, auto mapping, turning, stopping, or SLAM path following is converted into motor commands through the motor control, which drives the time 3 PWM channels. Free RTOS coordinate the pipeline by giving time-sensitive sensing and communication work predictable execution slots, while queues decouple fast interrupt or DMA producer from slow phaser, mapping, Bluetooth, and navigation consumers. In conclusion, our project demonstrated a coherent embedded ARM product running fully on the STIM32 platform, which achieved onboard LiDAR sensing, gyro-assisted audiometry, occupation grid mapping, autonomous exploring telemetry, and user interaction as a one integrated system.